What's cracking, guys? In this video I'm covering this new paper called Fake It Till You Make It, Face Analysis in the Wild Using Synthetic Data Alone, by these awesome people from Microsoft. And I actually had the privilege of working with them while I was back at Microsoft. So as a quick disclaimer, I actually did contribute a little bit to this framework, to this synthetics framework, and so I know a lot of details of how this project was structured and everything. In this video I'm gonna only tell you, obviously, only the things and conclusions you can deduce from the paper itself. So having said that, these guys are Errol Wood, Tadas Baltrushaitis, Charlie Hewitt, Sebastian Giaggio, Matthew Johnson, Virginia Estellers, Thomas Cashman, and Jamie Shotton. So let's see what the hype is all about. They say here that we demonstrated it's possible to perform face-related computer vision in the wild using synthetic data alone. So I mean, obviously you want to use synthetics if that's possible because you have perfect ground truth, but what was the problem so far? Well, there is something called domain gap, and I think it's fairly obvious when you try and train your models on synthetic data and then try to do inference with that same model on real data, you're gonna have some problems. The reason is you have different distributions. In the case where your synthetics is not perfect, as it usually is not, you basically have a gap because the distribution between those data points from the synthetics is different from the distribution of the data points in the real data. And so different people, different groups try to solve this in different ways. And some good examples would be like OpenAI. So I recently, a couple of months ago, covered this OpenAI's paper where they used the robotic hand to solve the Rubik's Cube. And the thing is, the PolicyDRL agent was actually trained purely in simulation. The approach they took was to not to try to create a perfect simulation, because it's even harder to create a perfect simulator for this robotic hand than to create a simulator for the faces, because here you only need to mimic the appearance of these faces, whereas in this case you have to model the physics, you have to model the friction, you have to model the contact forces, which is super hard to do. And so what they did is just randomize the simulations so that the real world appears like just another instantiation of a simulation. So they modify even stuff like gravity from the usual 9.81, at least on Earth, to like even 8.5 or whatnot. But it was all done gradually in order to have this curriculum, like a gradual training. So that was one approach. Second approach, other approaches were stuff like you can fine-tune on real images after training on your synthetics. So you have imperfect synthetics, you fine-tune on real data from the target distribution, and then you can expect that the accuracy or whatever metric you care about is going to improve. And finally, there are approaches such as upreeling with GANs, whereby you take your real data and you pass them through certain GANs, which will make those images appear more realistic. Those are all the different ways to try to reduce this domain gap. So Microsoft, on the other hand, took another route, and that's to reduce the domain gap almost down to zero. And we have to have some bad jokes on this channel, so yeah. Basically, here are some of the images that the framework produces. You can see they are fairly realistic, especially this person here. You can see that you can have geometry, so 3D information, because you have a synthetic data, and that means you also have perfect labeling, which is awesome, which is a superpower of this whole framework. You can do pixel-wise, semantic segmentation, you have the landmarks, however dense you want them to be, and a lot of other ground truth data, which we're going to see a bit later. Before I dig deeper into the paper, let me just show you this quick clip from Microsoft where you'll see the animations of this synthetics framework.
Here are some example synthetic faces that we render as training data for machine learning. With synthetic data, you can guarantee perfect labels without annotation noise, generate rich labels that are otherwise impossible to label by hand, and have full control over variation and diversity in a dataset.
Awesome. So let's continue and dig deeper into this paper. So they say here that they show that the synthetic data can both match real data in accuracy, as well as open up new approaches where manual labeling would be impossible. Okay, so a quick remark here. You need to keep in mind that rendering only face images, so the heads of humans, is a fairly constrained problem. I mean, you have like a certain geometry that all humans have. We usually have 2 eyes, we usually have 1 nose, and I mean, the problem is very, very constrained. And I really believe that we can actually reduce the domain gap almost down to 0, if not to 0 in the future, for this particular problem that Microsoft deeply cares about. So because the team works in mixed reality and virtual reality, so that means they care about stuff like Microsoft HoloLens, and there are other competitors out there such as Magic Leap and Facebook Reality Labs, and all of them care about this very constrained problem of like understanding human faces and bodies. And so the point I'm trying to drive here is that if you had some other area such as like self-driving, I'm fairly sure this is not the way ahead, because I mean, it boils down to the question whether it's easier to build up a new world or just understand the current world. Because in order to build a perfect simulator for self-driving, you literally have to cover so many edge cases, etc. So you literally have to build something like, I guess, real-world simulator. And yeah, I'm fairly sure that's harder than just trying to build computer vision systems that will solve self-driving. Continuing on here. When they say that when faced with a machine learning problem, the hardest challenge often isn't choosing the right machine learning model, it's finding the right data. And this reminds me strongly of Andrew Ng's data-centric approach. And the thing I notice here is that all of these people and groups that are focused more on short-term products tend to say something like this. And I don't mean that in a bad way. I just think that like this obviously implies supervised learning paradigm, and I'm fairly sure that's not the way that kids and humans learn. And I'm fairly sure that approaches that, for example, Facebook and DeepMind are pushing, like a self-supervised paradigm, is the way to go long term. But having said that, again, I think this is a fairly good approach at the time being, because we're going to build a better product which will enable us accelerate accomplishing those long-term goals of cracking intelligence. Obviously, they mentioned some benefits of synthetic data here. So with synthetic data, you can guarantee perfect labels without annotation noise, generate rich labels which are otherwise impossible to label by hand. And they have an example later here in the paper. Let me show you. Basically, I mean, you can generate as much landmarks as you want. Like you can make the mesh as dense as you want, and this is obviously not possible to achieve by manual labeling. It would be super expensive and super error prone. So that's some of the benefits that synthetic data is bringing. Let me go back here. Aside from that, you have a full control over variation and diversity in a data set, which is also very important when we are deploying these products globally. You want to make sure it works on different demographics. And they even have a histogram down here. Let me quickly show you this. So they show the histograms here over the age, over the, I guess it's sex, not gender, and ethnicity, and as you can see here, it's a work in progress, obviously, but the good thing is you can basically improve this, whereas it's way harder to do this when you're trying to collect real data. I guess a small remark here, it'd be nice to have like a ground truth histograms here, i.e. the global statistics, so that we can compare how far away is this current histogram from the actual desired target histogram. So this is another superpower of having synthetics. You can be very flexible and make sure that the training data is representative and mirrors the true statistics you wanna target. Okay. So let me show you how the data is actually like synthesized on a high level. What they do, you have this template face, you add the identity, then you add certain expression like smiling or whatnot, then you add the texture, you add the hair, clothing, sometimes they add like headwear, eyewear, whatnot, like devices. Again, that's something that Microsoft cares about, like think HoloLens. And finally, you add like the environments. You can see the lighting, you can see the background, etc. So that's on a high level how these models are 3D avatars are produced, and then you just render whatever you want by positioning a virtual camera in this scene. So a thing I want to stress here is this one. So it requires considerable expertise and investment to develop a synthetics framework with minimal domain gap. So this is another reason I think this is not the way to go ahead, but it's a perfect strategy for Microsoft in particular. This is super expensive to build and maintain, and etc. So on the pro side, say you have spent time labeling face images with landmarks. However, you suddenly require additional landmarks in each image. Relabeling and verifying will take a long time. If all of a sudden you realize you want to have additional landmark on the lip, you'll have to literally take all of your images and send them back to labelers so that they can relabel those images, and you have to verify that you haven't introduced any mistakes by doing this. So you can see this is very time consuming, very expensive, and erroneous, I guess. Secondly, synthetics lets you render faces from a simulated device to develop algorithms and even guide hardware design itself. Imagine what would be the alternative here. So you'd literally have to design a prototype, which is super expensive and slow process, and then you'd have to collect data, and only then can you train the model. On the flip side, with synthetics, you can literally just position in a scene. You can just position a virtual camera, and you can start rendering data, training models, and you can see whether it makes sense to position the sensor right there or not. So this significantly reduces the time it takes you to iterate, and so that's a huge asset. So you may ask yourself, what is the thing with this framework? We are already used to seeing amazingly realistic avatars in movies, in games, etc. And they give an answer to that here. So the visual effects industry has developed many techniques for convincing audiences that 3D faces are real, and we build upon these in our approach. However, a key difference is scale. So this framework proposes a procedural way to generate these avatars way more quickly and very realistically. So that's the value proposition of this whole thing. And now let me kind of break it down for you how the models are created. So we saw it on the high level here. Now let's see how they actually construct these identities, expressions, etc. So the main point here is they basically collected a lot of these scans. And to acquire these, you either have to buy them or have the space for collecting the scans yourself. So the thing is, those setups are very pricey, because I don't know if you ever saw one. I'm gonna pop it somewhere on the screen here. You basically have to have hundreds or if not thousands of cameras placed in that room in order to collect like the accurate geometry and everything you care about, and later various processing algorithms to form these scans. Additionally, obviously, you have to have real humans here in the loop, so it's a slow procedure, it's very expensive procedure. But once you have scans, they additionally had to do the cleaning step, so that's a very manual and very slow procedure to create from this raw scan to get this clean scan. Once you have the scans, you can construct something called template face. We're gonna see that in a bit. Then you can learn a generative face model, and then you can sample from that face model to obtain various geometry. Now let's see a bit more about the generative face model itself. So you basically are trying to create this generating function. So the formula does look a bit intimidating, and there is some domain expertise involved here, but on a high level, in order to form a novel geometry with a certain expression, what you do is you take this template face, which is formed as, and they mention it here, as the average face with neutral expression. So you take all of the scans, you find their vertices, you just do the average, and you find the template head. Then what they do is they learn this basis, and they call it the linear identity basis. They learn that thing, and finally you have this expression basis, which is not learned. Okay, once you have the template head, once you have this linear identity basis and the expression basis, you just use the betas and psis to determine the actual geometry of the face. And you can see here, so the generating function comprises out of, takes as an input betas, psis, and thetas. So theta just determines the position of the face model, namely one of those is like jaw. So you can basically position jaw something like this. And finally, once they fit so as I said, this S is learned, and betas are also learned so that they fit the scans that they have in the data set. Once they have a set of betas, they can fit a multivariate, a normal distribution on top of it, and that's how they actually form the generative model. And then you can just sample betas from it, and you can get novel identities. Continuing on, I want to stress again that this is a huge engineering project, more so than research. And they say here that in addition to facial expression, we layer random eye gaze directions on top of sampled expressions and use procedural logic to pose the eyelids accordingly. So there is lots of heuristics all around the place here, and not only for the like positioning the eyes, but also here for texture. You have to you basically use the scans to get the texture information. And they also say here that they are modeling here at the strand level. And so modeling here at the strand level allows us to capture realistic multipath illumination effects. But on the con side, each asset was authored by a groom artist who specializes in creating digital hair. So as you can see here, this is very slow and very expensive. Same goes for every other part of this synthetics framework. So you have to, obviously somebody has to construct these clothing, somebody has to construct the hats, the eyewear, etc. But at the end, because this is synthetics, you can have various types of labels. So not only vertices, which they later we'll see the results. They are doing a lemma regression. You can also have UVs, you can have masks, you can have depth, normals, albedo, every single type of information you can care about in computer vision and graphics. And again, they just showcased the variety of faces you can generate using this synthetics framework, and I think it's very impressive. Finally, let's jump to the actual results. This is where they stress that this data-centric approach makes a lot of sense, because for the semantic segmentation problem, what they've done is used simplest off-the-shelf models such as UNet and such as ResNet to build to get results which are comparable with state-of-the-art methods on these benchmarks. So for the semantic segmentation, what they do is they use UNet model, and they just apply the binary cross-entropy loss on the ground truth labels, which again are perfect because we have synthetic data. And the second thing that has to be done here is something called label adaptation. And let me first motivate what it is, and then I'm going to quickly explain how they do it. So the thing is, if you concentrate really hard on these images, you can see that, so this is the ground truth from the real data, and you can see that the nose here, it's fairly arbitrary decision for the labelers in this real data to kind of end the nose here. So basically this boundary of the nose is fairly arbitrarily chosen, and so we shouldn't penalize synthetics for having chosen that the nose ends here instead of here, and so that's why the adaptation is done. And what they do is they just freeze the weights of the first UNet, and they just what they do is they take the real data labels, and they just kind of map using another UNet. So this is basically another UNet, and you just map from the output from this synthetics model, you map to the real data. Let's jump to the final results. Let's see the tables. So this is basically for the semantic segmentation problem. You can see they compare their methods against various SOTA baselines, and you can see the results are fairly comparable here. So 92 F1 score against these baselines. Some of these baselines are a bit better. You can see that this paper in particular is 1.2 points better, but you need to realize that that model looks something like this. So you basically have pyramid pooling here, edge perceiving, edge-aware graph reasoning, edge-aware graph reasoning here, decoder, fairly complex reprojection projection. So it's a fairly complex architecture. Zooming into this particular module, you can see you have graph convolutions, transpose pooling, etc., etc. So very complex architectures. Whereas here they just use simple UNet, which is off-the-shelf model, and they achieve comparable results. So that's cool. Second thing is, what confused me initially was that we have better results with synthetics compared to real data, and I guess the main reason here is this particular data set. So they used Helen data set. I think it has around 2K training images, whereas I think they used 100K images to train the UNet, so that's why they get better results here. Although it'd be really nice if they explicitly mentioned that somewhere, that the amount of images used for this synthetics baseline synthetics results compared to the real result. And here, on the other hand, on this different data set called LEPA, the situation is a bit different because the real training data set actually has way more data points. So the results here are better compared to synthetics data set, and that makes sense. They also show results on the landmark localization and against some other SOTA results, and they show again that they have comparable results. So the synthetics data again here, some of them do have better results, like this one here, or I don't know, like this one here, etc. But like again, keep in mind they are using off-the-shelf models here. It'd be very, very interesting to see how this performs with much better models. They did some ablations. The augmentations matter a lot. So I forgot to mention that once you render data, what they do is they apply various augmentations like grayscaling, blurring, warping, etc. And they just show here that not using augmentations hurts performance by a lot. You can see the jump here. And finally, not doing the label adaptation hurts the performance a lot. So you can see here it jumps to 5.61 where we want to be lower. So it jumps from 3 to 5.6, which is a big gap. So that means this part is very, very important for landmark localization. Again, the reason is the same. There is also ambiguity, same as with semantic segmentation and the nose example here in the landmark localization problem. They have one more interesting visualization here, and they say here that predictions by networks trained with real, so that's the top one, against synthetic data on the bottom one. And they say that know how synthetic data network generalizes better across expression, illumination, pose, and occlusion. You can obviously see the results here are way better compared to the results up here. It's maybe a nit, but like claiming that you generalize better, whereas you have much more data using synthetics compared to real data, is not a fair claim, although I guess it proves the point that it's better to have synthetic data because you can generate as much data as you want. Yeah, and finally, let's end up here. I mentioned that the superpower is you can generate as much as dense landmarks as you want. You can basically put virtual sensors wherever you want and render. So for example, eye tracking is something very important for the HoloLens device. And so you need to be able to track where the pupil is, where the eye is, and you can quickly iterate with different positions of the cameras. Later, when the prototype actually is developed, you can be confident that the conclusions you draw from the synthetics experiments can now be generalized to the real data, and that's the superpower of this whole framework. Having said that, they clearly acknowledge certain limitations. We do not include expression-dependent wrinkling effects, so realism suffers during certain expressions. Since we sample parts of our model independently, we sometimes get unusual but not impossible combinations, such as feminine faces that have a beard and stuff like that. So yeah, I mean, again, this is an awesome result. I think this for this particular problem that Microsoft and some of these companies like Magic Leap, etc. care about, this is a perfect, I think this is a right direction to head into to build better products. But like if we were trying to just talk here about improving research, improving AI as a field, I think this is definitely not the way to go ahead. Finally, they mentioned that they are going to publish for non-commercial use case 100,000 images. And I saw some people were confused on Twitter, including Andrei Karpati, and I thought maybe trying and giving an answer to that like question. Namely to why they're only publishing 100K images. And the answer lies pretty much here. I mean, they took a look at, they did ablation for the landmark localization task, and they noticed that after 100K images, basically they get diminishing returns, and you can see the mean error starts increasing again. So that means 100K is totally arbitrary value, and the whole point of this framework is to have this flexibility that I just explained here. So even when they render all of these avatars from a certain angle, I mean, the whole point is you want to be flexible enough to put a new virtual camera and then re-render the data there. There is not much point in actually, in my opinion, in publishing these images. So what would be really nice is if Microsoft were to make an API out of this and earn some money by doing that, and help other people like not have to go through the same procedure that's, as we saw, was very expensive, very slow to create this whole framework. But I can also totally understand the reason for not doing that, because it was super expensive and it's giving Microsoft an edge. Anyways, if you like this paper, share it out with a friend. Subscribe to this channel, join the Discord community. We have very smart people chatting there, and you can ask them questions. So yeah, until next time, bye bye.